pressure. What do we say that two things will depend that affect pressure? The two things that affect pressure, right? Yes? Force and area. Is our weight a force? Is our weight a force? Yes, our weight is a force. Who is exerting this force on us? Earth. Earth is exerting a force on us. We are exerting a force on Earth. It's known as a gravitational force. And for us, all of us, we have different weight. So we have different forces acting on us. So here we have pressure is defined as the force acting per unit area. Like we mentioned, the bags. The bags that we talked about last week. The heavier the bag, the greater the pressure. What makes a bag heavy? The amount of things you put inside. The more things you put inside, the greater the mass, the greater the weight. And weight is a force. So that is why pressure is dependent on the force. Then this part about per unit area. You will see in physics, it happens very often. Per unit something. Have you heard of this phrase before? When? Acceleration, okay, so blah blah. Acceleration, rate of change of velocity, right? Per unit time. Right? And then your speed, rate of distance change per unit time. It is always per unit. I hope by now you realize that every time they say per unit, they are telling you to divide. You realize that? Okay, so over here what do you think is divided by what? Based on definition, definition is a string of words. It is a sentence. Definition is a sentence. Most of the time in physics, your definitions are related to a formula. So if you don't know how to study smart, for pressure, right, you will memorize two things. You will memorize, the definition of pressure, force per acting per unit area. So you memorize one thing, memorize. Then after that, what is the formula? Then you go and memorize the formula. E equals to F over A. Wow, so many things to memorize. But if you are smart, you will realize that we can get the formula from the definition. You memorize this one, you get the formula. Understand? So what do you think is the formula for pressure? Force divided by area, that's it. Okay, later we will talk about it. The pressure between two solid surfaces. So solid surfaces, they are all around us. Depends on the force between the surfaces and the area of contact between the two surfaces. So mathematically, this is the formula. Okay, do you want to memorize this? You don't need lah, as long as you memorize the previous one, the definition, then this one automatically will come out. Okay, but if you think you have too much time, too much capacity, go ahead and memorize. Why wouldn't? Okay, now the next one, SI unit. SI unit, what do we see over there? N/m squared. What do you make a guess? Okay, wait. What do you think the M stands for? Meter. Then if you put a square, then that's the unit for, what is the unit for? Area. Square meters is the unit for area, isn't it? That's what it means. See the slash over there, it also means divide, isn't it? Just like your distance divided by speed. Distance divided by time, you get meters per second. That's the unit for speed, right? Hang on. So I'm still talking about the m squared. So square meters, that's for area. What about the n over there, the capital N? What does it stand for? What does it stand for? Newton. It is a unit for. Yeah, you can't remember, right? Then based on formula, you obviously must be the unit for force, right? Because you're taking force divided by area. So Newton will be the unit for force. You can write it as Newton per square meter. That is the unit for pressure. Can you imagine having to write Newton per square meter, and then every time I ask you, you answer me Newton per square meter. Is that allowed to say? Newton per square meter. Six syllables, right? A bit long lah. So we can shorten it to PA. PA stands for pascals. Okay? It is a unit for pressure. PASCALS. Pascals. Is that easier to say compared to Newton per square meter? Okay, but you must know that they are exactly the same thing. So capital P, small a. Cannot be small p, small a. Cannot be capital P, capital A. Must be capital P, small a. Always. Alright? Just like our Newton is always capital. Our meter is always small. Okay so far? Can Then we get on to calculation already. For 11, calculate the pressure acting on the ground or in both cases. So you see, we have two boxes over here, A and B. Looking at the size, right? Do they look the same size? The amount of space they occupy, they look the same, right? But what can you tell me about the weight? Which one heavier? A or B? B is heavier. What about the base area? Are they the same? Yeah, they're the same. Using your own layman knowledge, pretend you never studied physics at all. One of these boxes is going to be placed on your hand. Which one exerts more pressure? A or B? B, right? Because A is lighter, so you feel less pressure. B is heavier. It has a higher, it will exert a higher, greater pressure. So it will be a bit more painful. Okay? Then you remember what is the formula for pressure? So P equals to F over A. Put them all in. Pressure equals to force over area. You can just write P equals to F over A. You can. P equals to F over A. Then for object A, the force 20, the area 0.5. Use your calculator. 20 divided by 0.5. 20 divided by half. Your math is good. It's 20 times 2. 40. 40 what? You want to write N per square M? Newtons per square meters? You can. Because we have 20 in terms of newtons. Then the area is in terms of square meters. You can. Alternatively, you can just write Pascals, PA. So this is the pressure for object A. Alright? What about for object B? Can you write down the next line? For object B, pressure equals to F over A. Then put in the values. Then I check. Pascals. Okay? So here, this is what we have. Who got this right? Raise your hand. Very good. Put a tick to indicate that, yeah, you got it correct by yourself without me telling you. So you have more confidence in your work. So what can we see from this example over here? You see the base area is the same, right? But one is exerting a greater force. The one that is exerting a greater force, but although they have the same area, the pressure is going to be different. Greater force, greater pressure. Any questions? Very logical, right? Common sense, Now we have two boxes again, but the base area is different. But we see that the weight, they're both the same. Is it possible to have two boxes, different size, but same weight? Is it possible? Yes, of course it's possible. Your bags all different size, but it's possible for them to have the same weight also, right? Okay, so this is a very reasonable case. But the base area is different now. 0.5 square meters and 0.2 square meters. Please calculate the pressure for both of them. Okay, so let's talk about common sense first before we review the answer. Which one, when placed on your hand, more painful? B. Which one more painful? B. A or B? Yeah, B. Why? Because smaller base area. So, but when you explain in physics, right, you cannot just tell me smaller base area. You must tell me the pressure is greater because the base area is smaller. Because the keyword is pressure, not just the base area, okay? So here is the answer for object A. Pressure 40 pascals again. Isn't it exactly the same question? Yeah, same, right? Okay, then for object B, the pressure, now we are dividing by a smaller number. When you divide by a smaller number, do you expect the answer to be bigger or smaller? Bigger. Maths tells you that. You divide by a small number, you get more. You divide by a big number, you get less. Exactly what this is over here. So same force, okay, same weight, but smaller area means greater pressure. Okay? Surface may rupture. What does rupture mean? What does rupture mean? Breakthrough. Okay? So for example, the notice board at the back is very ruptured with a lot of holes. You want to go and staple, you rupture it, right? You put a thumbtack, you rupture it. Your skin, can your skin rupture? Yes. Yeah, when you go for an injection, rupture your skin. So we say that we can push a pin into a board because the tip of the pin has a small area. Hence, the pressure is high. Understand what this means? Okay, now, I think I shared with this class at the start when we talk about physics. The force that I am able to exert generally will be the same, right? My maximum force today and tomorrow is about the same, isn't it? Today, do you think if I use my maximum force, can I pierce this pen into the notice board? Oh, you want me to try? Okay, let's make it more realistic. Let's make it more realistic. Needle. If I use my maximum force, can I pierce the needle through the notice board? Can, right? Maximum force, If I use my maximum force, can I pierce the chair through the notice board? Okay. Let's make it let's do it this way. Okay, this one. If I use my maximum strength, do you think I can pierce this water bottle through? Who say can? I'm not that strong, sorry. Okay, I cannot. Although my maximum strength is the same, I can very easily pierce the needle through, but I cannot pierce this water bottle through. The reason is because of pressure. The needle has a smaller pressure, has a smaller base area. So the amount of pressure that I exert, although my force, always remember F over A, force over area. Although the force stays the same, when the area is very small. How small? Close to zero. Divided by such a tiny number, the pressure is very high. So I can rupture this, I can pierce through. When the area is so big over here, when I divide by such a big value, the area over here, my pressure is lower because I divide by a big number. So the pressure lower, I cannot pierce it through. But maybe if you get a bodybuilder or somebody really, really strong, they may be able to do it because they exert more force than me, isn't it? Okay? Yeah, okay, maybe it's a trial, I don't know. So this is the whole idea behind pressure. Makes knife. Very easy to slice through, isn't it? And it is easy because the force exerted by our hand is distributed over a small area. That's why it is easy, the pressure is high, you can slice through it easily. But what if the knife is light? Yeah, sometimes, I don't know whether you try to use a blunt knife, right? You try to cut orange, then the skin will kind of bend in instead of cut because the pressure is not high enough. Yeah. So, these are some common applications of pressure. Next example. An elephant weighing 50,000 newtons. You see, when we talk about weight in physics, what is the unit? Newtons. When you step out of the classroom, somebody else asks you, what's your weight? Maybe they are doing a health survey. Ask you, what's your weight? You're going to tell them in terms of kg or newton. If the person went through secondary school, and then you tell him in terms of newton, right? I think he's trying to be funny, right? At least, but he knows what you're talking about. If it is somebody who didn't study physics, you tell him, oh, I am physics, when we talk about weight, it is in terms of newtons. I haven't teach you how to convert from newtons to kg yet. So just take it that this elephant has a weight of 50,000 newtons. That's a lot, obviously. And it stands on 1 foot of area 0.1 square meter. What is the pressure exerted by the elephant on the floor? Okay, calculate. Calculate. When the elephant is on 4 feet, it's standing normally, do you expect the pressure to be higher or lower? Huh? Lower. Okay. Who agrees with Dexter? Lower. Who disagrees? I think it's higher. Anybody thinks it's higher pressure? No. Okay. Since all of you agree, then why is it so? Why is it that when all 4 feet are on the ground, the pressure is lower? Greater base area. So we divide by a bigger number, right? Pressure is now lower. Okay? So that's for this question. In this case, we have a woman of weight 500 newtons. Less or more than the elephant? Less, right? By how many times? The elephant was 50,000 newtons. So 100 times less. Okay? Is it realistic or 100 women equal to 1 elephant? Okay lah, quite okay lah. She's wearing high heel shoes. Assuming that the total area of the heels is 1 square centimeter. Realistic or not? Have you seen high heel shoes? Just the heel, the tip, 1 square centimeter. How much is 1 square centimeter? Can you imagine how much is 1 square centimeter? 1 square centimeter. So that's 1 centimeter times 1 centimeter, right? Right? So you take a ruler, you see 1 centimeter times 1 centimeter. So you draw a square, right? That is the size of the heel. Does it make sense? It does. Okay, hang on. So glass. The girl over here, she has the total area of the heels. Total area, so both. Okay, total 1 square centimeter. So 1 heel is half square centimeter. What is the resultant pressure on the floor? You know how to calculate this? Force over area again, right? Okay, so let me show you the answer. Okay, hang on. You listen. Here we have the woman, both feet on the floor, right? So it must be the total force. Total force is her weight lah. She cannot change her weight, right? Unless go on diet lah, or eat more lah. But for now, we don't think so much. Her weight is constant. Then they already said the total area of her heels. So you don't have to bother whether it is standing on 1 foot, standing on 2 feet. They already tell you total area is 1 square centimeter. So you don't have to divide. Because total area already. So you divide, you get 500 newtons per square centimeter. Any question?
Does that mean that she's standing right on the heel?
Yes, in this case she's standing on the heel. Very strange that one. Just take it. Hey, you all are not asking physics question anymore. You all are asking about how realistic the question is. Can we just take it that for the sake of this discussion, let's just take it that this is realistic. Okay? Here, newtons per square centimeter, is it the same as pascals? Who thinks? No, they are not the same. No? Okay, who thinks they are the same? Okay, what is now the answer? We said that pascals is the same as newton per square meter. Right? Newtons per square meter, or SI. Okay, here we have per square centimeter. So they are not the same anymore. Wait. Are you dying to find out who is exerting a greater pressure? Well, is the woman exerting a greater pressure or is the elephant exerting a greater pressure? Is it the elephant? Do you have the same units? You do have the same units, right? So you cannot conclude yet. You need to convert this in order to find out whether they are the same or greater or less. So, has your physics teacher, meaning me, taught you how to convert from square centimeter to square meter? Yes, I have. Okay, so let us convert in SI unit. So this will be in terms of Newton per square meter or in Pascals. So we start by converting 1 square centimeter to square meter first. Because eventually I want square meter, right? So from 1 square centimeter, it is actually 1 cm times 1 cm. So 1 square centimeter is actually 0.01 meters times 0.01 meters. You get 0.0001 meters. Can? Okay so far? Now that we have this, can you convert to SI units already? Can you convert the pressure exerted by this woman on the floor? So same formula. Pressure equals to force over area. But instead of 1 square centimeter, we are not going to use 0.001 square meters. Then your answer will be in terms of Pascals. Then it will be the same as elephant. Then you can compare. Okay, so use your calculator right now, find out what the answer is. So here, we have the same formula. Force divided by area, we get 5 million Pascals. 5 million. Now, which pressure is greater? The one exerted by the elephant or this woman? This woman, apparently, according to the figures provided by this question, this woman is exerting a greater pressure. Alright? Yes, you all feel that it's not very realistic. How can a woman stand on 2 heels only? But is it more realistic if the woman just balances on 1 heel just for a short while? Can or not? That one can accept? Okay, just for that short while. The pressure higher or lower than the elephant? Higher lah. Okay? Done with the answer? Can I move on? Yes? Can't hear you. 5 million newtons per square meter or Pascals. 5 million, 5 followed by 6 zeros. Okay. Part C. Explain why such shoes cannot be worn on wooden flooring. Is there anywhere in our school that has wooden flooring? Oh. Okay. Last. Who knows how to swim? Swim. Who has tried diving down deep before? Try to touch the floor at the bottom. Okay, now put your hands down. Who has tried, put your hands down first. Who has tried doing it at a 1.8 meter pool? Go and touch the floor. Okay, I tried it when I was young. Wow, quite scary. But how do your ears feel anything? What was the word you said? Pressure. As you go deeper and deeper, you experience more pain in your ears, right? Okay, now, do you know that there is fluid in our ears that allows us to roughly tell whether we are upright or are we going to fall? Okay? There is some fluid in our ears that allows us to tell whether we are standing upright or not, whether we are going to fall or not. And that's beside the point, but when we go and dive, the deeper you go, the more water there is up there, right? Water has mass, isn't it? Water has weight. All that weight is acting on you, on your ears. So can you imagine if you go deeper and deeper, it's like somebody sticking a finger into your ear and pressing, exerting a force, it's the same. The water is exerting a pressure on your ear so you feel uncomfortable. But it is not just on your ear. It is on your skin also, right? All over you. It's just that your ears are more sensitive. Now what happens if you go deeper and time it is the opposite. Okay, class, listen to me. This time it is the opposite. Sometimes when you take a lift up very quickly, you feel it also. Sometimes you take a lift from very high down, you also feel it. That is because your ears inside, in addition to fluid, there is also air inside. Okay? When you go up into the sky, the pressure up there is higher or lower? What do you think? What do you think? Air pressure up there higher or lower? Lower, because less air on top, more air at the bottom, right? So the air pressure at the bottom is higher. The air pressure when you climb mountain, air pressure very low. So the air inside your ear will expand. You'll push out. Because low pressure out there, high pressure inside, so you'll push out. Then you feel a bit of pain also. Okay? Then the pilot, he will switch something that adjusts the air pressure in the aeroplane. Okay? Why if they don't? Then I think you will all feel very uncomfortable. When you pop your ear, you are trying to equalize the pressure. Okay? Now, why did I say all this? Class, we are now going to introduce you to atmospheric pressure, the atmosphere. So the air around us exerts pressure on all objects that are exposed to air. So there is air pressure acting on all of you right now. Air pressure. So it acts in all directions, every single direction, and the pressure exerted by the air in the Earth's atmosphere is called, obviously, atmospheric pressure. So if it is exerting pressure on, for example, your water bottle, if there is air pressure exerted on it, why isn't it crushed? Right? Okay, force is not strong enough, but there is also air inside water bottle, right? When you do that, you are exerting more pressure, so you crush it. Right? Now, normally your water bottle doesn't crush by itself, because there is also air inside a bottle that is exerting the same pressure outside, yes.
So if you vacuum the air out of the bottle, it will just come out.
If you vacuum the air out of the bottle, you have a plastic bottle, right? Can you demonstrate all together? Plastic bottle, you try and suck the air out. Okay. Or you drink the water, but you won't let the air go in. You don't do, you just drink. Okay? Okay, see what's happening to the bottle. Is it crushed? Yes, right? Okay, thank you very much. It is being crushed. By who? Who is crushing it? The air around us is crushing it. Listen. It is not that she's crushing it deliberately. She's just drinking. She's removing the air and water from the bottle. So the air pressure on the outside will proceed to crush it. Then the moment she releases, then the air will go inside, right? Then you will push it back out. It will equalize again. Yes? You feel like your mouth is getting stuck in the bottle because there is originally space in the bottle. Then as you suck out the air, yeah, then your mouth will go inside, take the space out. Exactly. Okay, so I need all of you to relate your real life experience with physics. And next time you go and try, if you go to a tall building, right, at the bottom of the building, you open your bottle, you close it, so that's normal, right? You take the lid up, then you try and open again. You see whether you will experience anything or not. You won't be so exaggerated, but you will feel. Okay? But it's not carbonated, plain water. Just plain water bottle, bring it up. Then you try and open. You will feel a change. Same thing, there will be a change. You will feel the change. Okay? Okay, so atmospheric pressure acting all around. How does a straw work? So all of you grew up knowing how to drink from a straw, but you know how it works. Alright, so now we're going to teach you. At the start, when you stick the straw into the cup, where is the water level? Same, right? the straw is the same water level. Then when you start to suck the air out into your body, originally there is air over here, isn't it? Originally got air. Then when you start to suck the air up into your body, is the air left, same or different? More or less? Less because you suck the air out, of course there's less air, right? If there is less air, you think the pressure will be the same? If there's less air, the pressure is going to be lower. Okay? If the pressure is lower, as compared to the pressure outside here, which is known as the atmospheric pressure, which acts in all directions. Your air pressure acts here, act here, act here, act here. It acts everywhere that is exposed. But if it acts on the glass, right, it doesn't do anything because the glass is quite strong, right? We don't expect to put a glass of water out there and then the glass starts to crumble. It doesn't happen because the glass itself is quite strong. But for this part, when the air pressure is acting downwards, originally, when you haven't started sucking it, right? Air inside here, air outside here. They equalize, same. But when the pressure here goes lower, the pressure here is now relatively higher, isn't it? Higher pressure outside, it will start to push down. So it actually pushes the water up. Therefore, it is not very accurate to say that you are the one who is sucking the water out. It's not very accurate to say that. Rather, what you are doing is you are sucking the air up. The air pressure, the atmospheric pressure is pushing the liquid into your mouth. Understand the difference? But you don't go and pour other people outside there. You know for yourself already. You know what's happening. Good enough. Okay? Any questions so far? Next time, when you drink water from a straw, you just think through it. Okay. Air pressure in the straw is lower, air pressure outside is greater, so it pushes it up your mouth. Don't need to go and tell other people because you'll bore them. But it helps in your own revision. Every time you think about it, it strengthens it. And it's not very difficult to understand, right? Then might as well just go through it until it becomes common knowledge to you. And when test you during the exam, no problem. Okay, so this one we talked about it already. Pressure in liquids. When an object is immersed in a liquid, the liquid exerts pressure on it. Common sense lah. It's just that on the Earth's surface, air pressure is exerted on us. When we go underwater, water pressure is exerted on us. So the water pressure. Okay. So the deeper it is, the greater the pressure. Common sense? The deeper you go, the greater the pressure. Therefore, there is discomfort in our ears when we dive deep. Have you seen deep water creatures before? Very, very deep, right? They look like monsters, right? They usually have a hard exterior, very tough, and they look really ugly. Now, when you bring them up, so let's talk about downstairs first. When they are at the bottom of the ocean, is there a lot of pressure on them? Yes? And they are used to it. So their body, right, will exert the same pressure outwards. So that they can equalize, Right now, my body is exerting an equal pressure outwards as the air pressure is on me. Otherwise, I'll be crushed. If I'm exerting more pressure on the outside, then I will get bigger and bigger, just like a balloon. If you blow in the balloon, you're pushing more air inside, isn't it? The air pressure is greater, so it will start to expand. When you release it, it will start to contract. Now, for the same creature under the water, it is used to the great pressure on him. He is exerting a great pressure outside. When you bring him up to the surface, what's going to happen to him? He continues to exert the pressure outside, and then you bring him out, what's going to happen to him? He will start to expand and become even more monstrous. Start to look like, don't know what. In the worst case, maybe it will explode. Okay? Alright, class. That's all for our pressure. There is one last part to this topic that will be tested. It is very easy. It is known as free body diagrams. Yeah, what's free body diagram? Basically, they are just boxes and arrows. Okay? Although I say this is easy, if you can get the concept, no problem. If you don't listen carefully and you miss out on the concepts, you're gonna be having a hard time all the way until you're Sec 4. So these are simply block diagrams with arrows to represent forces acting on the body. They do not represent distance. They do not represent mass. They represent force. They represent forces. Okay, done? Okay, so in reality, let's say we have a book on the table. All of you have items on the table. There is weight acting down on the table, isn't it? Okay. So if there's a weight acting down, shouldn't it start to sink and go past your table and all the way to the floor? Because there's a force acting on it, what? Right. But we don't see that happening. You put a bottle on the table, it stays on the table. Why isn't it going down and down and down? Why? There is a force downwards. So why isn't it going down? Not that it is not enough force. There is a force upwards as well. This force in red is known as the normal force. Okay? In the first part of the topic, we talked about the contact forces. So this normal force is what is happening to your bottle. It's what's happening to me. When I'm standing on the ground, I'm exerting a force on the ground. The ground is at the same time exerting a force on me. It is exerting the same amount of force on me as me exerting on the floor. That is why I am not sinking to the ground. That is why I'm not floating up. Sorry? You mean when you are jumping? Styrofoam. Okay, that's because it is softer lah. Okay, like you stand on a mattress, you will sink down, right? So that is due to the pressure. Okay, so for now, we are concerned about drawing. You must be able to translate the diagram on the left to the diagram on the right. Does it look difficult? For the book, you represent it by a box. We always use a box. Then we have arrows to represent forces. Now in this case, how many forces are there? Quite clearly there are two arrows, so there are two forces. One downwards, it is known as the weight. Where do we start drawing the weight from? From the center of the box. Okay? Then next, we have the normal reaction force. Must be the same length, huh? Must be the same magnitude. If one arrow bigger than the other, it means that either the box is flying up or the box is going downwards. Why it is stationary? So must be the same length, so they're equal, but different direction. Then because the red line, the normal reaction force came from the table. It is pointing upwards. So at the bottom of the box, we draw upwards. Okay, this diagram so far? Then I move on. To draw the free body diagram, we first determine the weight, which is a force. Then the center of gravity. Center of gravity. Next, we identify the contact forces. Remember what are contact forces? All the push and the pull, you push somebody, then somebody pull you, contact forces, okay? What? Oh, okay, remove one of the forces. So contact forces and the point of contact. So what we have over here, we also must identify the non-contact forces, such as the weight. You know, the earth doesn't need to touch you in order to pull you closer to the earth, right? Right? So that's a non-contact force. But for things like friction over here, must have contact, then you can have friction. So those are contact forces. So you must identify all the forces. Then next, the object is always represented by either a square or a box. Doesn't matter. No circle, must be a box or a rectangle. So let's talk about this case. This person is jumping down the bungee jump. Okay? At this point in time, is the rope taut? Is the rope taut? That means is it very straight? No, right? So is there tension? No tension. There's no pull. Okay? So what are the forces acting on this person? Okay, let's talk about what direction is this person moving in? Downwards. So there is a force acting downwards. That's gravity, right? Gravitational force is known as the weight. Yes. So for this person, this is the only force acting on this guy. So the rope doesn't apply any force on the bungee jumper at this position. So if I were to draw a free body diagram, it's just a box with one arrow downwards only. Okay? Compared to your bottle on the table. There are two forces, right? One down, one up. Then I say if there's only down, then your bottle will be going down, right? But that's not the case. In this case, for the bungee jumper, there's only one direction downwards, so the person is literally going down. Now the moment it is taut, when she reaches or he reaches the minimum point, the rope is straight, right? It is now taut. There is tension already. So there is still the weight. The weight will always be there. The weight, you cannot get rid of your weight one. Always will be there. But there is a pull upwards. So at this instance over here, if the forces are the same, then it's going to stay there already, okay? If the magnitudes are the same. But we know that in reality, it's not the case, because it's going to be bouncing up and down, right? To simplify things, if they are the same over here, it's going to stay the same. Alright? The magnitudes are the same, but opposite direction. So the free body diagram for the person on the way down, a box with an arrow down. Do you have that diagram? Okay, please draw this one for a free body diagram. Your arrows you must use ruler, unless you're so sure that your arrows are very straight. Okay, then you must label also. You must label the forces, which is weight over here. So far, easy? Easy? Easy. Yeah, easy. Okay, next one. When the person is at the bottom, then we've got a weight down still. The person doesn't lose the weight. And we also have a pull upwards. This time, the pull is at the top of the box. Imagine the person is being held by the legs, right? The legs are up there. So the force starts from the top upwards. But the weight will always start from the center of gravity. In a box, it is very easy. Center of gravity is just in the center. Okay? When we have irregular things like this visualizer, where's the center of gravity? Very hard to tell. So we use boxes to represent, make things easier for us. Okay? Done with this? Who needs more time? None. Helicopter hovering in the air. Stationary position. Woodlands are a lot of helicopter because of Sembawang Air Base, right? Helicopter in the air stationary. Imagine that happening now. Okay, can you imagine? Does helicopter hovering in the air have weight? Got weight or not? So must have a force downwards, right? Then shouldn't it be coming down? Then how is it hovering? There is a force acting upwards to make it equal. So there's weight down, this force is called lift. Okay? So when we simplify with a box, it makes things easier. Weight down, lift up. So same for aeroplane wings, they allow the aeroplane to generate lift. That brings it up. Yes, draw it at the top of the box because the lift actually comes from the rotor blades. Right? So they are at the top. So draw it at the top. Doesn't make sense for the lift to start from the bottom lah. But like I said, the weight will always start from the center of gravity. That one is confirmed. Okay, done? Next. A box is being pushed on and slides on a rough floor. So if this diagram, I am pushing from the right to the left, right, I push. So you see the arrow starts from the right side. The arrow can pass through the box one, no problem. It just tells me where I am pushing from. Understand what I'm saying? Where is friction? Because they say rough floor, right? There's friction, isn't it? Yes. What direction? Opposite. Because the definition of friction is that it will oppose or tend to oppose motion. If I'm pushing to the right, then friction, this friction I always want to go opposite direction. So in the other side. Then should we start drawing the friction from the top of the box or bottom? Why bottom? It's a contact force. It's in contact with the ground. So this is the contact point for the push, and now friction, we start from the center of the box. Friction in the opposite direction. And we just take the center as the contact point. Okay? Simplify things a bit. The things to take note of is that friction starts from the bottom, and if you are doing a push, it starts from the side. Common sense so far? Quite common sense, right? Huh? Okay, what about the weight? So this is the free body diagram. It looks like this. There is a weight, you are right. Which I didn't draw over here because I'm just concerned about left and right direction. If you want to draw in the weight, go ahead. Draw the weight downwards. Then you must draw your normal contact force up. Okay? Any questions? But for now, if I'm just talking about push and pull, the weight is not relevant in this question. Okay, next one. Ball flies vertically upwards after being kicked. So you kick, it flies upwards. So it is still moving up. What are the forces acting on it? Which one confirm have one? Confirm will have weight, right? What is the direction of the weight? Downwards? Yes? Okay, so that is the first force. What is another force acting on it? Air resistance. As it goes up, there will be air resistance pushing it down. Okay, because air resistance is like our friction. It always goes in the opposite direction as us, as the direction of motion. So for Greg, when he runs very fast, he experiences a lot of air resistance. So there are techniques to run. Okay, you don't run with your hands like that and you try to catch a lot of air, right? Right? You try to be as aerodynamic as you can to reduce air resistance. So the free body diagram looks like this. Air resistance pointing down, weight pointing down. But what direction is the ball traveling? What direction is the ball traveling? Up. The ball can be traveling up, but all the forces are pointing down. Take some time to think about it. Okay? The ball is going up, but all the forces are acting down. This is possible. But the ball, as it is going up, it is slowing down, right? And eventually it will come down. Throughout the whole journey, the weight is always acting downwards. When it is going up, the air resistance is just a little bit pointing down. When it is coming down, what is the direction of air resistance? Upwards, just a little bit. It always tries to resist a little bit. Okay? Yeah, so that it will slow down. So next question, box mass, 0.5 kg on a rough surface. Free body diagram. Now I'm going to tell you how to convert from mass to weight. From mass in kg to weight in newtons, just times 10. Okay? So my weight is 700 newtons. What is my mass? 71. 70 kg. You know your own mass. You know how to find your own weight now. Just times 10. Okay? So here we have the box of weight, 5 newtons downwards. Following so far? Okay? Then it rests on a rough surface. Is it moving left and right? It is not. So friction is not an issue over here. Then there is a normal contact force upwards, 5 newtons also. You must label your forces. Your normal contact force will start from the bottom. And it must have the same magnitude, same length. Yes, write it as F normal. Otherwise, I don't know, unless you want to spell normal contact force. Do you prefer that? I suppose you prefer the right letter, F normal. That's good enough. F stands for force. Okay, so normal contact force. Faster finish? Okay. Now, part 2. It is pull. Yes? What? I didn't start from the top of the box. I started from the bottom for the normal contact force. Okay, next one. It is now pulled along the rough surface. 10 newtons to the right. Okay, so if you are being pulled, we start from here. Common sense, I start pulling from one side. So it doesn't cut through the box anymore. We are pulling, we are not pushing. So this is the horizontal force of the box for the pull. But at the same time, there is friction. 4 newtons I never tell you the direction, no? So which direction is it? Opposite, which is the left. So friction, like this. These are the horizontal forces acting on the box. Okay, so our friction must be at the bottom. And because it is 4 newtons, it is smaller than the pull. So overall, right, what direction, which one has a greater effect, left or right? Right, yes, you're right. Then if we indicate all the forces acting on it, it's as such. Okay? So these are the 4 forces acting on it. Hands over. Am I going too fast? Am I clicking too fast? But don't worry lah, you can watch it online. Then you can slowly draw. Because the next part is more exciting. It's resultant forces. This one, tug of war, who will win? No, just this left or right, who win? Or can tell or cannot tell? Cannot tell, I don't know who is stronger. Okay? Now, we don't know just by looking at the picture. What if now I tell you that on the left we've got 110 newtons to the left. On the right we've got all these. Who win? Right side, because you add all of them up. Total force to the left, 110. Total force to the right, how much is it? 170. So who win? Right side. What is the net effect? What is the overall effect? I've got 110 to the left, 170 to the right. What is the overall effect? You move to the right by how many? Or rather, what is the resultant force? 60 newtons to the right. Yes, you're right. That's it. That's our resultant force. So you are expected to be able to come with this working over here. There is 110 to the left, 170 to the right. Overall, the word is called resultant. Will be 60 to the right. Okay? Is the maths over here easy? Very easy. I show you the next few examples. You will use it. You will finish it really quickly. Why the values are different? Okay, it's not that more people will win. If these are the forces, to the left 180, to the right 120, then it is 60 to the left. Common sense, right? Okay. What if it is 180 to the left, 180 to the right? Who win?
No one.
Nobody win. It is a draw. What is the resultant force? 0. It stays that. There is no resultant force. It is 0. Okay. It's a tie. So here we have resultant force. Okay, fill this in. Just add up. So here I say assign direction to the right as positive. So to the right is positive, to the left will be negative. Okay, so that is 14 newtons to the right. This is equivalent to only a 14 newtons force acting to the right. Understand this diagram? So you see how with the free body diagram, it makes things easier for us. I don't have to care whether it's a car, whatever it is, I just know it's a box. That's good enough. Do you think you can do the rest of the... Okay, so this is the equivalence. 8 newtons and 6 newtons is equal to 14 newtons to the right. Okay. Do you think you can do the rest yourself? How many pages are there?